Hey everybody, today we are looking at a fascinating paper that is shaking up the world of the synthetic data generation for alignment data. The guys at the Allen Institute for AI and the University of Washington have developed a method called MAGPIE that generates high quality and diverse synthetic data, prompting Instruct LLMs with nothing. And let's see what we mean by nothing. So we are looking at the paper. It's called MAGPIE Alignment Data Synthesis from Scratch by prompting align LLMs with nothing. It basically tries to solve one of the main issues with the open source data creation methods, synthetic data creation methods. And it's basically that they don't scale. Basically, it's really difficult to scale the size of the data sets. Usually, as the size of the data set increases, the diversity decreases. It requires also curated data, high quality curated data. So you could use those data points as seeds and then generate new data from those seeds. So the current methods have some limitations. So the authors of this paper ask themselves, is it possible to synthesize high quality data, high quality instructed data at the scale, but by extracting that data directly from an aligned LLM? So as we know, we have basically base LLMs, and then we have instruction data, and basically we do fine tuning. We fine tune that LLM to have, let's call it like a chat LLM, right? We have open weight LLMs like Llama 3, for example, Llama 3 chat. We can use those LLMs for inference. We can fine tune those LLMs on downstream tasks. The problem is that companies like Meta don't release the datasets. So it's really difficult for the open source community to catch up and create extracting data as good as the data that these companies have produced. So the idea here is, okay, if we come up with a method that doesn't need human intervention, doesn't need seed data, we don't need to curate any data from high quality sources, would it be possible to extract actually this data directly from the LLM without these constraints? And that's what the authors of this paper ask themselves. So they call this method a self-synthesis method because, as we said, it doesn't need human intervention, doesn't require seed data. So it's a sort of cell synthesis involved in generating that large-scale alignment datasets. The good news is that they observe that these strong aligned LLMs like Llama 3 Instruct, for example, can generate really high quality and diverse user queries when you are actually just passing a left side template up to the position reserved for the user message. If you're not familiar with the chat ML template that is used for nowadays for aligning these models, you basically have some sort of pre-query template. Could be like start, header, ID, then you'll have the user, and then you have and let's call it a header, ID, and then basically that's how this template look like. I think there is there is here diagram where you could see much better. Or you have a start header ID, the user, and header ID. So, but just passing the left side of this pre-query, the model automatically generates diverse and high quality user queries because it has learned that during instructing fine tuning, basically. And basically, they are using this method for generating what it seems to be quite large, high quality alignment dataset. Let's look at it, actually. As we said, one of the main challenges in constructing alignment datasets that researchers have faced are that one of the methods that are used relies on human effort, basically. So old-fashioned method, let's hire some labelers, let's generate data according to some guidelines, some annotation guidelines. The problem, obviously, is that it's extremely time-consuming. It's labor intensive for sure. And apart from that, we've seen in many cases that humans, especially if they are not domain experts, they do struggle to generate complex data. So usually the data is quite at the lowest level of the complexity scale. So that's something to consider. It seems that LLMs are much better at producing more complex data. The second method that the researchers have been using is using obviously LLMs to produce synthetic data, but starting from a set of manually curated seed instructions. And the problem there is that, as we already introduced, the diversity of the synthetic data tends to decrease as the dataset size grows, and that's obviously a problem. Yeah, so that's why the authors of this paper wanted to come up with a data creation method that doesn't require humans and doesn't require seed data. Let's look at this diagram, the figure 1 here, that illustrates the process of self-synthesizing instructed data from an aligned LLM. It's important that the LLM that you're using should be aligned already. You cannot really use a base model because it hasn't learned to produce that. Since, obviously it's not aligned. It hasn't seen that user query data at all. First step is generating the user query. And as you can see here, the first step, we input the left side template, the query. We pass it to the model. That's just our prompt, and then it's going to generate an instruction. What material should I use to build a nest? These are what they call random queries. So if you pass the same pre-query template again, you're going to get a completely different instruction. If you send it again, you're going to get a different instruction. That's the cool thing about it, that you are actually generating diverse data without starting from seed instructions. And then the second step is, as you could imagine now, is like for that query to generate a response using the same LLM, basically. So what materials should I use to build a nest? Okay, building a nest, that's a wonderful project, etc., etc. And that's how they create the dataset. That's how they create the alignment data. Yeah, if we look a little bit more into the details, they are saying that they observe that when you input the pre-query template to an aligned LLM, it could be like Llama 3 Instruct, it could be, I don't know, QN272V Instruct. As long as you use the right pre-query template, that's important. You need to use the same pre-query templates, so the same special tokens that were used for aligning that LLM originally. You cannot use the wrong ones. These LLMs, since that they self-synthesize a user query, they are saying that this is due to the autoregressive nature of these models, of the transformer model. These random user queries are of high quality and great diversity, and to be honest, this is surprising. This is quite one of the coolest thing about this method, in my opinion. They think that this is due to the abilities learned during the alignment process that are now effectively utilized by passing that pre-query template. So they use this method for constructing two different datasets. One is called MAGPIE-Air, that was constructing using the Llama 3 8B Instruct model. And the other one is MAGPIE-Pro, that was constructed using a model of the same family, but much larger. In this case, Llama 3 70B Instruct. They are sharing as well the computational resources that they needed for creating these datasets, which is pretty cool. For MAGPIE-Air, using Llama 3 8B Instruct, they needed around 206 GPU hours. And for MAGPIE-Pro, they needed more hours, 614 GPU hours. But again, let's emphasize this, they didn't require any human intervention or API access to production LLMs like GPT-4. They didn't need to use closed source proprietary models. And actually, it's possible to adapt this method to create also multi-turn instruction datasets. We'll see it later, how you could adapt the pre-query template to create terms. They generated similar datasets, MAGPIE-Air MT and MAGPIE-Pro MT. We could take a look at some of the statistics in this table 1. If we compare it to other popular alignment datasets, like for example, synthetic datasets. We can take a look at, like Evolve, Instruct. We can see that Evolve, Instruct, and UltraChat pack as well, one of the most popular ones, synthetically generated datasets. We can see that actually, let's look at MAGPIE-Air, is actually much larger compared to this. It's a different order of magnitude. It didn't require any human effort at all compared to these other three datasets that, even if the human effort required for this was low, still require a little bit of effort from us, basically from humans. Important difference as well is that these datasets employ these proprietary models, and here they are just using open weights LLMs like Llama 3 in this case. So let's take a look at how you could basically extend the method. Let's go to the appendix. I think it's F. Yeah, appendix F, prompt templates. Let's look specifically at figure 11. So this is the prompt that they use for creating multi-turn datasets, basically. They are adapting the method so you can produce conversation terms, and that's what the prompt that they use. Yeah, it's kind of a prompt, but yeah, not a lot of prompt engineering required here. So as you could see, we are passing beginning of text token, special token, start header ID. Then we are telling the model, okay, this is a system. And in the system, they are actually setting the context, explaining that this is a multi-round conversation with the AI, with the LLM. And by doing this, they are able to generate, multi-turn datasets, as easy as that. So you could imagine that you could do the same, but for perhaps trying to set the topic or the domain. And that's what they are actually saying, that you could try to control the instruction tasks. As we can see here, you are an AI assistant designed to provide helpful step-by-step guidance on solving math problems. So we are setting the domain or the topic. So we want to generate user queries about mathematical problems. Still a bit uncertain how this would scale, and if the LLM would actually still produce high diversity data, but since it's possible. Let's look at the datasets that they generated, and how they explore the dataset, how they analyze it. So they tested the dataset coverage. They analyzed the coverage of in this case, the MAGPIE-Pro dataset in the medium space using SNE, sorry. And they compared it with datasets like Alpaca, Evolve, Instruct, and UltraChat, the other datasets that we saw that they were synthetically generated. And it seems that from the plot, the MAGPIE-Pro actually has quite a good coverage. Let's take this with a grain of salt. We know that the SNE could be misleading at times, but since that it covers at least the same topics as the ones covered in these datasets. Yeah, they are saying basically this suggests that MAGPIE-Pro provides a broader or more diverse range of topics, highlighting its extensive coverage across varied themes and subjects. Okay, since that the coverage is good, let's assume the coverage is good. And then they run some dataset attributes analysis. The first one is the task category of instructions. What they did is they prompt Llama 3 8B to categorize the instances in the dataset. Since that, for example, information seeking is the predominant category. And yeah, I think that makes sense. We know the type of data that it's usually in those alignment datasets, because normally you have users actually seeking information, right? When they prompt LLMs, when they work with AI assistants, so it makes sense. Then we have another attribute called quality of instructions. I don't think I would trust this one a lot, but let's see. What they did is basically they used Llama 3 8B Instruct to assess the quality of each of the instructions generated by the model. And then, yeah, they are kind of saying, okay, most of the user queries are average and good or excellent. Yeah, but considering that they use the same model for generating that data, that they don't really know, let's say they don't really know the definition of quality that the model has learned. I wouldn't trust this a lot, to be honest. It gives you like a very, very high level kind of idea of the quality, but what good quality is for this Llama 3 8B Instruct model could be very different from what a human understands as good quality. Okay, it's like a cheap way of defining a quantitative metric for quality, but I wouldn't trust it a lot, to be honest. Same with the attribute difficulty of instructions. They took a similar approach. Basically, they use Llama 3 8B Instruct model to rate the difficulty. Yeah, it's interesting that in this case, for the model, it's always easy, pretty much. Yeah, not sure about these attributes. I'm not sure I would have done the same, to be honest. This one, I like it more, instruction similarity. Basically, they are using the minimum neighbor distance in the embedding space. And basically, they are seeing like the distribution here. Okay, this is another figure, like the figure V is different. Yeah, it's more interesting, instruction similarity, to see that you are actually generating different queries, basically, and it's based on embeddings. I think could be trusted a bit more than the other ones generated by Llama 3 8B. And then we have the last attribute, quality of responses. And here they took a different approach. I think I like it more. They use a reward model to calculate a reward difference. And if the reward difference was positive, then that means that the response from the dataset is of higher quality. And that's a good sign. So I think I like this more. We can see how the instruct reward is actually, since it's high, is more positive compared to the base reward. So we like that. Finally, let's see how they evaluated this method. So what they did is, okay, they created these data sets, and what they did is fine-tuning. They fine-tune these LLMs and compare them on some of the most common benchmarks. They compare this fine-tune LLM to other LLMs fine-tune on different data sets, like, for example, LLM fine-tune on Ultra Chat, right? And it seems that if we look at the table 2, it seems that the model fine-tuned on the MAGPIE data actually outperforms the other models. For example, Alpaca Val 2, this model MAGPIE fine-tuned on Pro through 100K data points is outperforming the rest of the models in the length control win rate. If you are interested in this, the length control win rate is actually a way that the authors of Alpaca Val 2 came up with to reduce the verbosity biases of GPT-4 when rating responses. So yeah, I'm not gonna go through the results in detail, but it seems that this model is actually outperforming other models that were trained on similar data sets. So yeah, the method seems to work. Something to consider is that it doesn't perform well on all the tasks in these data sets. As we can see clearly, math and data and coding and debugging, these are clearly weaknesses. It's probably data that you could generate by just prompting with the pre-query template without actually telling the LLM anything. It's not going to generate mathematical data or coding data for alignment. And you would probably need to try control the instructions a little bit by, as we saw, passing that system message in the per-query template. But it seems that generates really good data for creative tasks, for reasoning and planning as well, and for information seeking. I hope you enjoyed this paper as much as I did when I was reading through it. If it's relevant to your work and you take it for a spin, let us know, and let us know if it really works and if it worked for your case. Thank you so much.